Welcome to Chapter 10 of Class 10 Science, The Human Eye and the Colorful World. In this fascinating chapter, we'll explore how we see the beautiful world around us and understand the optical phenomena that create the colors we experience every day. Have you ever wondered how your eye works like a camera? Or why the sky is blue and sunsets are red? We'll answer these questions and more as we study the structure of the human eye, common vision defects and their corrections, the magic of prisms creating rainbows, and the atmospheric effects that make stars twinkle. This chapter connects our understanding of light from previous chapters to real-world phenomena, helping us appreciate the incredible science behind our everyday visual experiences. Get ready for an eye-opening journey through optics. Let's begin with the amazing human eye, nature's perfect camera. The human eye is one of our most valuable sense organs, enabling us to see the wonderful world and colors around us. While we can identify objects through other senses when our eyes are closed, we cannot perceive colors without vision. The eye works remarkably like a camera. It has a lens system that forms images on a light-sensitive screen called the retina. Light enters through the cornea, which does most of the refraction. The iris, the colored part of our eye, acts like a diaphragm controlling the size of the pupil, which regulates how much light enters. The crystalline lens provides fine adjustment for focusing. The retina contains millions of light-sensitive cells that convert light into electrical signals sent to the brain via the optic nerve. The brain then processes these signals to create the images we see. It's incredible to think that the image formed on our retina is actually inverted, but our brain automatically corrects this so we see the world right side up. Now let's explore the eye's amazing ability to focus, called accommodation. The eye lens is made of flexible, jelly-like material whose curvature can be changed by ciliary muscles. This changes the focal length, allowing us to see objects at different distances clearly. When we look at distant objects, our ciliary muscles relax, making the lens thinner and increasing its focal length. When we look at nearby objects, the ciliary muscles contract, making the lens thicker and decreasing its focal length. This automatic adjustment is called accommodation. However, there are limits to this ability. Try reading a book held very close to your eyes. You'll find the text blurred and experience eye strain. The minimum distance for comfortable, clear vision is about 25 centimeters, called the near point or least distance of distinct vision. The farthest point we can see clearly is infinity for a normal eye. As people age, sometimes the lens becomes cloudy, causing cataracts, but vision can be restored through surgery. Sometimes the eye loses its power of accommodation, leading to vision defects. The three main refractive defects are myopia or nearsightedness, hypermetropia or farsightedness, and presbyopia or age-related farsightedness. In myopia, a person can see nearby objects clearly but not distant ones because the image forms in front of the retina. This can be due to excessive curvature of the lens or an elongated eyeball. Hypermetropia is the opposite. Distant objects are clear but nearby objects are blurry because the image forms behind the retina, caused by the lens focal length being too long or the eyeball being too small. Presbyopia occurs with aging as the ciliary muscles weaken and the lens becomes less flexible. The good news is that all these defects can be corrected using appropriate spherical lenses, concave lenses for myopia and convex lenses for hypermetropia and presbyopia. Let's focus on myopia, or nearsightedness. A person with myopia can see nearby objects clearly but cannot see distant objects distinctly. Their far point is closer than infinity, maybe just a few meters away. This happens because the image of distant objects forms in front of the retina instead of on it. This defect arises either due to excessive curvature of the eye lens or elongation of the eyeball. Myopia is corrected using a concave lens of suitable power. The concave lens diverges the light rays before they enter the eye, ensuring that the image focuses exactly on the retina. For example, if a person has a far point of 80 centimeters, we would use a concave lens that forms an image at 80 centimeters for objects at infinity. Calculating the power using the lens formula gives us the exact prescription needed. This simple correction allows myopic people to see distant objects clearly again. Now let's examine hypermetropia, or far-sightedness. A person with hypermetropia can see distant objects clearly but cannot see nearby objects distinctly. Their near point is farther away than the normal 25 centimeters. They might have to hold reading material at arm's length for comfortable reading. This occurs because light rays from nearby objects focus behind the retina. This defect arises either because the focal length of the eye lens is too long or the eyeball has become too small. Hypermetropia is corrected using a convex lens of appropriate power. The convex lens provides additional converging power, bringing the focus forward onto the retina. For instance, if a person's near point is 1 meter instead of 25 centimeters, we would use a convex lens that forms an image at 1 meter for objects at 25 centimeters. The calculated power gives us the prescription that enables comfortable reading in near vision. Presbyopia is an age-related condition where the eye gradually loses its power of accommodation. For most people, the near point gradually recedes away as they age, making it difficult to see nearby objects comfortably without corrective glasses. This happens due to the weakening of ciliary muscles and diminishing flexibility of the eye lens. Sometimes people suffer from both myopia and hypermetropia, requiring bifocal lenses. These special lenses have a concave upper portion for distant vision and a convex lower portion for near vision. Modern alternatives include contact lenses and surgical interventions like LASIK. It's also important to remember the noble cause of eye donation. Our eyes can give vision to up to 4 blind people even after our death. Eyes must be donated within 4 to 6 hours after death, and many people with corneal blindness can be cured through transplantation. Now let's shift our focus to prisms and the beautiful phenomenon of dispersion. A prism is a transparent optical element with inclined refracting surfaces. When light passes through a prism, it bends in specific ways, unlike a rectangular glass slab where the emergent ray is parallel to the incident ray. The angle between the incident and emergent rays is called the angle of deviation. Through careful experiments with prisms, we can trace the path of light and measure these angles. What's truly fascinating is that when white light passes through a prism, it splits into a beautiful band of colors. This is called dispersion. The sequence of colors is always the same: violet, indigo, blue, green, yellow, orange, red, remembered by the acronym VIBGYOR. This happens because different colors of light bend through different angles when passing through the prism. Red light bends the least while violet light bends the most. The most spectacular natural example of dispersion is the rainbow. A rainbow is a natural spectrum that appears in the sky after rain showers. It's caused by the dispersion of sunlight by tiny water droplets in the atmosphere. For a rainbow to form, the sun must be behind the observer with raindrops in front. Each water droplet acts like a small prism. Sunlight enters the droplet, refracts and disperses into colors, reflects internally inside the droplet, and then refracts again when exiting. Different colors reach the observer's eye from different droplets, creating the beautiful arc of colors. Isaac Newton was the first to systematically study dispersion using prisms. He proved that white light is composed of 7 colors by using a second prism to recombine the spectrum back into white light. Any light that gives a spectrum similar to sunlight is called white light. Now let's explore atmospheric refraction, the bending of light as it passes through Earth's atmosphere. This explains several fascinating phenomena including the twinkling of stars. Starlight undergoes continuous refraction through layers of air with varying densities before reaching our eyes. Since the atmospheric conditions are not stationary, the apparent position of stars fluctuates, and the amount of starlight entering our eyes flickers, making stars appear to twinkle. Planets, however, don't twinkle because they are much closer and appear as extended sources rather than point sources. The variations in light from different points average out, canceling the twinkling effect. Atmospheric refraction also causes advanced sunrise and delayed sunset. We see the sun about 2 minutes before actual sunrise and about 2 minutes after actual sunset because the atmosphere bends sunlight around the Earth's curvature. Finally, let's understand scattering of light and why the sky is blue. Scattering occurs when light is deflected by small particles. The Tyndall effect is the scattering of light by colloidal particles, making the light path visible, like sunbeams through forest canopy or headlights in fog. The color of the sky is due to scattering by air molecules and fine particles in the atmosphere. These particles are smaller than the wavelength of visible light and scatter shorter wavelengths more effectively. Blue light has shorter wavelength and is scattered about 10 times more than red light. This scattered blue light enters our eyes from all directions, making the sky appear blue. At sunrise and sunset, sunlight travels through more atmosphere, scattering away most blue light and leaving red and orange light, creating beautiful red sunsets. This is also why danger signals are red. Red light is scattered least and can be seen from longer distances.